Hello, and welcome to a short series of lectures about the way that mathematicians think about infinity. I hope it to be very accessible to anyone with a high school level math background. You don't need to have taken calculus. It will help to have some familiarity with the abstract notion of a function, but I will review that material when I come to it. So this is a lecture series about infinity. You may have formed an impression about infinity from your math classes in school that infinity is not a very serious thing to think about, that you can't do the ordinary algebraic sort of operations with it, you shouldn't ever divide by infinity or multiply by infinity, and so on, that it's not a number. Although I hope to convince you that it is a serious thing to think about, and I hope to show you why there are mathematicians who spend all their time thinking about it. Some of that impression is true. Infinity is not a number in the sense that it's not a real number. You won't find it on the number line. But in another sense, it is a number in that it's the answer to the question of how much of something there is. So if someone were to ask you how many whole numbers are there, how many numbers are on the number line, how many possible computer programs there are, how many points in space, how many triangles in the plane there are, and so on, what are you to say but that there are infinitely many? So the first question that you have to grapple with when thinking about infinite sets is, how do you know when two infinite sets have the same size? And what could this even mean? In our everyday lives, when we have two finite sets and we want to know that they're the same size, we simply count the elements of one of the sets, count the elements of the other set, and then compare the two numbers that we got. So for instance, if I want to know that the number of chairs in my classroom is the same as the number of students in my upcoming class, I can simply count the chairs in my classroom, and then I can count the names on my enrollment sheet and compare those two numbers. The other thing that I could do is that I could invite my students into my classroom and invite them to take a seat. If after all of them have chosen a chair, I notice that there are no vacant chairs and that each student is seated in his or her own chair, then I know that the number of students and the number of chairs is identical, because my students have provided me with a pairing between the elements of the set of students and the elements of the set of chairs. One chair has been partnered with one student, and one student has been partnered with one chair in a sort of one-to-one exclusive way. Let's look at another example, a slightly more mathematical example. Suppose that I have 5 people. Now consider the number of ways there are to form a pair, to form a group of 2 people from among this set of 5 people. So here's one pair, here's another, here's another. How many different ways are there to do that? I don't know. But consider also the number of ways there are to form a group of 3 people. So here's one group, here's another group, and so on. So then we have another quantity, the number of ways to form a group of 3. I don't know what either of these numbers is, but one thing I can be certain of is that these two quantities are identical. Why is that? Because anytime I form a group of 2 people, I sort of implicitly form a group of 3 from the people remaining. And vice versa, anytime I form a group of 3 people, I form a group of 2 from those remaining. So every group of 3 has a partner in the set of all groups of 2, and vice versa. And this pairing is sort of exclusive in that each group of 3 determines a unique group of 2 given by the remaining members of the group. So I can say that these two quantities are the same because I paired the elements of the two sets. And I can know that these two quantities are the same without actually knowing their value, without actually counting either of the sets. So once again, the moral is that to establish that two finite sets have the same size, it suffices to simply put their elements in a sort of one-to-one pairing. And it turns out that this is the right way to think about infinite sets as well. So let's look at an infinite set. The most important infinite set for us is going to be the set of positive whole numbers, which mathematicians write with an n whose first vertical stroke is doubled. And they call this a set of natural numbers, although also I'll try to say positive whole numbers. So this is 1, 2, 3, 4, etc. Sometimes people include 0 in this set, but I will not. I want to ask whether this set has the same size as a set of negative whole numbers. I'll denote this with a minus sign. So this is minus 1, minus 2, minus 3, minus 4, etc. So do these two sets have the same size? Well, if by that question we mean, does there exist a pairing of the elements of the two sets in the way that we paired students with chairs, in the way that we paired groups of 2 with groups of 3, then obviously the answer is yes, because we can pair 1 with minus 1, 2 with minus 2, 3 with minus 3, and so on. And in general, we pair the number n with the number minus n. So on the number line, this pairing looks like this. So as a consequence, what we say is that the size of the two sets are the same. So we say that the size of n, set of positive whole numbers, is the same as the size of minus n. We also write this quantity, we denote this, the size of n. In this way, we write the set, and then we write these vertical lines around it, sort of like absolute value signs. So let's look at another example, much more famous example. Let's first consider the set that we saw earlier of positive whole numbers. Now consider the same set, but delete the number 1. We write this n minus the set containing 1. So this will be 2, 3, 4, 5, etc. All the positive whole numbers strictly greater than 1. And now I want to know if these two sets have the same size. It may surprise you to learn that they do. Why should that be surprising? Well, note that the bottom set sort of sits inside of the top set in the sense that every element of the bottom set is an element of the top set. So here we have a set of positive whole numbers. So 1, 2, 3, 4, etc. And inside of that, we have the set on the bottom. This set, positive whole numbers greater than 1, so it's this set. So the bottom set here sits inside of the top set here, but it's not all of the top set because there's this element 1 that's not included in the bottom set. This may lead you to believe that the bottom set is actually smaller than the top set, but in fact we can pair the elements of both sets in a one-to-one way. And if you've never seen this before, I invite you to stop the video and think about how this could be done. So the way to do this is suggested by the ordering. You look at the first element on the top, number 1, and you pair it with the first element on the bottom. That's 2, so 1 is paired with 2. Look at the second element on the top, that's 2, pair it with the second element on the bottom, that's 3. 2 gets paired with 3, 3 gets paired with 4, 4 with 5, 5 with 6, and so on. And in general, the element n will get paired with n plus 1 on the bottom. As I said, the bottom set sits inside of the top set. We denote this using this sort of sideways cup symbol with a line under it, and we say that the bottom set is a subset of the set on the top. And because the set on the bottom is not the entire set on the top, that is, that there's an element on the top that's not in the set on the bottom, we say that the set on the bottom is a proper subset of the set on the top, and we denote that with a little equality sign with a line through it on the bottom of the cup. So the surprising fact that a proper subset of a set, n, can have the same size as n is actually a feature of all infinite sets, and it's actually a way to define what it means for a set to be infinite. So a set is infinite if and only if its elements are in one-to-one correspondence with some proper subset of itself. This particular example is sometimes illustrated using this imagery of a hotel. In fact, it's a thought experiment called Hilbert's Hotel. So one imagines that there is a hotel that has infinitely many rooms, numbered 1 to infinity. And we assume that the hotel is fully occupied with guests. So there's one guest in every room. And now imagine that a new guest comes along and requests a room. Now the question is, can you as the hotel manager accommodate this new arrival? So if you've never seen this before, you might like to pause the video and think about how you might do that using the idea that we saw previously with the one-to-one with the pairing between a set of positive whole numbers and a set of positive whole numbers without 1? The answer is to instruct that each current guest of the hotel relocate. So you request that each guest move up 1 room. So the person in room 1 will go to room 2, the guest in room 2 will go to room 3, the guest in room 3 will go to room 4. And this is suggestive of the pairing that we just saw. If you think of the current guests of the hotel, these green stick figures, as being numbered 1 to infinity, then what we're doing then is pairing them with the set of rooms whose numbers are greater than 1. So the first guest will get paired with the second room, the second guest will get paired with the third room, the third guest will get paired with the fourth room, and so on. And at the end of this process, you will have created a vacancy because the first person will have moved to room 2, the second person will now occupy room 3, the third person will occupy room 4, and the first room will be vacant. And so our new guest can be accommodated there. So now the next thing you might ask is, what if we have a fully booked hotel, fully occupied hotel, as before, with infinitely many rooms, numbered 1 to infinity, and now we have not 1, but 2 new arrivals who request 2 separate rooms. So there are 2 different ways to think about this problem. One is that we take the guests one at a time. We know how to accommodate the first new arrival. We do that by simply asking everyone to move down a room, and then we put the new arrival into the first room. At the end of that process, the hotel looks like this. And we have 1 more new arrival to accommodate, so we just repeat the process. Again, ask everyone to move down, place the second new arrival in the first room. The other way to do it is to accommodate them both at the same time by asking everyone to move down, every current guest of the hotel to move down by 2 rooms. Not 1 room, but 2 rooms. So 1 will go to 3, 2 will go to 4, 3 will go to 5. And at the end of this process, the first 2 rooms will be vacant to accommodate the 2 new guests. And obviously this generalizes to a case where you have any finite number of new arrivals. And so the next question to ask is, what if you have infinitely many new arrivals? So once again, we have a hotel, all of whose rooms are occupied. And now we have an infinite number of new arrivals. The current guests we can number from 1 to infinity using the positive whole numbers, and let's say that we can do the same with the new arrivals. And all these new arrivals want individual rooms. How can I accommodate them all? So if you've never seen this before, I invite you to pause the video and think about it. The solution is to ask the current guests to double their room numbers. So the person in room 1 will be asked to move to room 2. The person in room 2 will be asked to move to room 4. The person in room 3 will be asked to move to room 6, and so on. And the result of this is that only the even number of rooms will be occupied by the current guests. The movement of the current guests, pictured in green, suggests a pairing between the set of positive whole numbers, 1, 2, 3, 4, 5, etc., represented by the guests and the numbers associated with them, and the set of positive whole even numbers, 2, 4, 6, 8, 10, 12, etc., represented by the room numbers that the current guests are asked to move to. So the first current guest is asked to move to room 2, the second current guest is asked to move to room 4, the third current guest is asked to move to room 6, and so on. And in general, the nth current guest is asked to move to room 2n. So this suggests that there exists a pairing between a set of positive whole numbers and a set of positive even numbers. So notice that the result of this is that all of the odd numbered rooms are now unoccupied. And we can now accommodate our new arrivals. So the first new arrival will go to 1, the second will go to 3, the third will go to 5, and so they'll occupy the odd numbered rooms. This, in turn, suggests a pairing between, again, the set of positive whole numbers given by the numbers associated to these new arrivals and the odd numbers, odd positive whole numbers, represented by the numbers of the rooms that they're asked to move to, 1, 3, 5, etc. So I'll write this set 2n minus 1. Now suppose that I had labeled the new arrivals not with the positive whole numbers, but with the negative whole numbers. So minus 1, minus 2, minus 3, minus 4, minus 5. So this would be the person whose label is minus 1, minus 2, minus 3, etc. Then we would have produced a pairing between the room numbers of Hilbert's Hotel, which remember just the positive whole numbers, and the set of all whole numbers with one exception, namely 0. So notice that every whole number on the number line, 1, 2, 3, 4, 5, etc., minus 1, minus 2, minus 3, minus 4, etc., with the exception of 0, has been accommodated in Hilbert's Hotel, meaning that we have a pairing between the set of positive whole numbers and the set of all whole numbers, excepting 0. So we assert that these two sets have the same size because we've produced a pairing between their elements. But now we'd like to accommodate 0 as well, so that we can say that the set of positive whole numbers has the same size as the set of all whole numbers. Well, we can do that very easily, as we've seen. Mr. 0 comes along and says he'd like a room. Well, we've already seen that we can accommodate him by asking all of the guests to move down a room. And when we do that, our hotel will look like this. So the consequence of this is that we've produced a pairing between the set of positive whole numbers, represented by the room numbers, and the set of all whole numbers, represented by the numbers of the guests. So we can say that we have this pairing between the two sets, and so the two sets have the same size. The set of all whole numbers, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5, etc., and also 0, is written with the letter Z. So this set is 1, 2, 3, 4, etc. This set is 0, 1, 2, 3, etc. and minus 1, minus 2, minus 3. Now we come to the most important definition of the first half of these lectures, and that's the definition of the notion of countability. If the elements of an infinite set, such as Z here, can be paired in a one-to-one way with the positive whole numbers, we say that that infinite set Z is countable. So if S is an infinite set and the elements of S can be paired one-to-one with the elements of our most important set of positive whole numbers, then we say S is countable. So in other words, an infinite set S is countable if it has the same size as the set of positive whole numbers. And a still more colorful way to say it is that an infinite set is countable if its elements can be accommodated in Hilbert's Hotel, with one element per room and no vacancies. I think you can see perhaps why we use the word countable, because in some sense we're counting the elements of the set. But for instance, let's draw the set Z on the number line. We've associated 0 with the number 1. So we've counted 0 as the first element. We've associated 2 with the number -1. So we've said -1 will be the second element. One is the third element. -2 is the fourth element. +2 is the fifth element. -3 is the sixth element. And so we're counting all the elements of this set one by one. So 1, 2, 3, then 4, then 5, then 6, then 7, then 8, and we're jumping back and forth. And we're counting the entire set, not in the sense that in some finite time we will have assigned positive whole numbers to all of the elements, because of course this process goes on forever, but in the sense that if you pick any particular element of this set of whole numbers, that number will eventually be labeled with a positive whole number by this process. So for instance, if you pick the number -100 way out to the left on the number line, this process will eventually count that number, and it will be assigned the number 200 as it happens. Now there are many ways you might try and fail to count this set. For instance, you may see this infinite set. So the previous examples we saw were sort of easy to count because the way to count was suggested by the ordering. So for instance, with these two sets, the orderings were the same. So we could pair the first element with the first element, the second element with the second element, and so on. Similarly, for these two sets, set of whole numbers and the set of positive whole numbers and the set of positive whole numbers without 1, we pair the first element with the first element, the second with the second, and the third with the third, and so on. But this new set, the set of all whole numbers, no longer has the ordering of the set of positive whole numbers. So if we had used something like the previous strategies and just imposed on this set the ordering of the positive whole numbers, just started counting 1, 2, 3, 4, 5, counting to the right, this strategy would not have counted the entire set because there would have been all of these numbers to the left that would have never gotten labeled by this strategy. So that's why we had to exercise some cleverness in counting this set. We had to do this sort of back and forth, balancing back and forth so that we counted everything. So the lesson is that counting infinite sets often requires a little bit of cleverness if they're not ordered in the same way that the positive whole numbers are. We've seen now that even if Hilbert's Hotel is fully occupied, it can still accommodate an countably infinite procession of new arrivals. The next question you might ask is, can we accommodate 2 infinite sets of new arrivals? As pictured? Well, we know how to accommodate a single infinite set of new arrivals. And at the end of that process, we find ourselves again with a fully occupied hotel and one more infinite set of new arrivals to accommodate. And so we just repeat the process. But how could we accommodate both sets of new arrivals all at once? So I invite you to pause the video and think about this question. The answer is to ask each current guest of the hotel to triple their room number. So the person in room 1 will move to room 3. The person in room 2 will move to room 6. The person in room 3 will move to room 9, and so on. And at the end of this process, only the rooms whose numbers are divisible by 3 will be occupied. So room number 3 will be occupied, room number 6 will be occupied, room number 9 will be occupied, and so on. Then we ask the first set of new arrivals, these red people, to occupy the rooms whose numbers are 1 more than a multiple of 3. So the first one will occupy room 1, the second one will occupy room 4, the third one will occupy room 7, and so on. Then the second set of new arrivals will occupy rooms whose numbers are 2 more than a multiple of 3. So the first one will occupy room 2, second one will occupy room 5, the third will occupy room 8, and so on. And we can picture this way of counting all of these guests as follows. We have the original guests of the hotel, then we have the blue guests on the second row, and then the red guests on the bottom row. And the way we counted all of these guests, we've said that the first red guest is number 1, the first blue guest is number 2, and the first green guest is number 3. So this is 1, this is 2, this is 3. Then the second red guest is number 4, the second blue guest is number 5, the second green guest is number 6. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we go on counting in this way. So the path that we sort of chart through this set of guests is looks like this. It looks like a zigzag. And in general, for any finite number of infinite processions of new guests, we can count these guests by charting a path using this sort of zigzag pattern. So we start at the bottom of the first column and work our way up until we've completed the first column, then we move back down to the bottom of the second column. Work our way up, move back down, and zigzag in this way. Now there are many ways to try and fail to count this set of guests. For instance, you might try just to count the first row and then move on to the second row. But if one starts counting the first row, one will be counting forever and will never get to any of the higher rows. So this is not a strategy for counting this set. So this is another case where one has to be sort of clever in the way that one counts the set. So now let's think about these guests as points in the plane, which is how they're sort of arranged in this way. So we think about the coordinate plane with the y-axis and the x-axis. So let's say we have 4 rows of guests, and we start counting in the way that we've discussed. So the point 1, 1 will be the first guest. The point 1, 2 will be the second guest. The point 1, 3 will be the third guest. Then the point 2, 1 will be the fifth guest. The point 2, 2 will be the sixth. We have the 7th, 8th, 9th, 10th, etc. And given some general point out here in the plane, say it's m, n, where m is an integer greater than 0 and n is an integer greater than 0 and less than or equal to 4, we want to know which number we're eventually going to assign to this particular point in the plane if we count in the way that we're discussing. So I invite you to pause the video and think about it. Well, each time we count a column, we use up 4 numbers. 1, 2, 3, 4, 5, then 6, 1, 2, 3, 4, then 5, 6, 7, 8, and so on. So by the time we come to the mth column, which is the column in which m, n appears, we will have used 4 times m minus 1 numbers to count all of the previous columns, and then we'll use n numbers counting up from the bottom to get to the y-coordinate n. So this will be the label that we assign to m, n when we count this set. Just for the sake of concreteness, I think it's good to see that there's a formula associated with the way that we count the elements of this set. So you give me any particular element of this set, let's say it's 100, 3, I can tell you what the label that I'm eventually going to assign to that element is going to be 4 times 99 plus 3. All right, well, what's the next question to ask? What's the next sort of level up in difficulty? What if we have not a finite set of infinite rows, but an infinite set of infinite rows? So we no longer have some finite set of rows, but now these rows extend infinitely upward in the plane. Well, before we were able to count the previous sets by starting with a particular column and just counting from the bottom, 1, 2, 3, 4, 5. But the strategy no longer works, because if we do that, then we're going to count forever and we'll never come to the second column. Nothing in the second column will ever be assigned a number, because we'll use up all of the numbers, all of the positive whole numbers on the first column. So I invite you to think about how we could possibly count this set, show that it's countable. And the hint that I would give to you is to tilt your head 45 degrees to the left. And when you do that, you may see a set that can be counted in the way that we counted the previous set. Okay, so when one tilts one's head to the left 45 degrees, you should see that the set that you're now looking at looks sort of like this. Now it's arranged into columns of increasing but finite size. The first column has 1 element, the second column has 2 elements, the third column has 3, the fourth has 4, the fifth has 5, and so on. And these columns can be counted one by one because they're all finite. We can start with this element, then we can move on to the second column and count its elements, then the third column and count its elements, the fourth, and so on. And each time we will eventually complete the counting of the column and move on to the next column because the columns are finite. So when one looks at the original set, one sees that the numbering that we're assigning is 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10. And so the path that we're charting through the set looks like this. It's a sort of a zigzag. So the name for the set that we just counted is n times n. It's the set of all ordered pairs of positive whole numbers. So m comma n, where m and n are in the set n, meaning that they're both positive whole numbers. And the consequence of the argument that we just gave is that this set n times n is countable. In other words, it has the same size as the set of positive whole numbers. So once again, we see that a set that looks vastly bigger than the set of positive whole numbers actually has the same size as the set of positive whole numbers. This set contains, in some sense, a bunch of copies of the set of positive whole numbers. 1, 2, 3, 4, 5. The first row is a copy of the set of positive whole numbers. The second row is a copy of the set of positive whole numbers. It has infinitely many copies of this set, and yet it has the same size as this very set. This set that we've been discussing, n times n, the set of all ordered pairs of positive whole numbers, is just one piece of a bigger set called the integer lattice, where you have one point at every point in the plane whose coordinates are a whole number, negative, positive, or 0. So we have this lattice extending everywhere through the plane at every point whose coordinates are whole numbers. So this extends on all sides. And now the question is, can we count this set? So what's a path that we could take through this set that would visit at every point, in the sense that if you pick a point, then at some point I will visit that point. and it will get a positive whole number label. So I encourage you to pause the video and to think about this. One possible solution is to do a sort of spiral pattern. Start at the center, at the origin, and you go out and you come around and you spiral in this way. So that means that the origin, the point 0, 0 is going to be my first element. Then the point 1, 0 is going to be my second element. Then 1, 1 is going to be 3. Then 0, 1 is going to be 4. Minus 1, 1 is going to be 5. Minus 1, 0 is going to be 6, 7, 8, 9, 10, 11, and so on. And in this way, we count the entire integer lattice. So we arrive at the conclusion that the integer lattice is also countable. So we write the integer lattice with this notation, meaning the set of all ordered pairs of whole numbers. So this is a countable set. So you may be forming an impression by this point that maybe every infinite set is countable. But I hope that very soon I'll be able to show you that that's not the case. But before we get to that, I want to show you a couple more countable sets. The first one is called the set of rational numbers. So a rational number is nothing more than a fraction of two whole numbers. A fraction of whole numbers, where of course with fractions we require that the denominator is not 0. So for example, 1/2 is a rational number, 7/22 is a rational number, minus 10/3 is a rational number. We also have the whole numbers because they can be written as whole numbers divided by 1. This is 5 is a rational number. 0 is a rational number because it's 0/1. So we write the rational numbers with the symbol Q with a line, with an extra line. So Q, the set of rational numbers, is the set m/n, where m and n are whole numbers, and n is not 0. So what does this set look like on the number line? So here we've got the number line, 0, 1. Well, as we said, it's got numbers like 1/2. It's got all the integers. It's got 3/2, that lives right here. It's got 5/2. It's got minus 1/2, and it's got minus 3/2. And it's got minus 5/2. And so on. And it's got a 4th. And it's got 3/4. And it's got 5/4. And 7/4. And 9/4. And 11/4. And so on. But it's also got an 1/8. And it's got 3/8. It's got 5/8 and 7/8. And 9/8. So you can see that these rational numbers are forming a sort of cloud, a dense cloud in the number line. And in fact, dense is a technical word for a property that the rational numbers have. And the technical meaning of the word dense is that for any tiny little interval in the number line, no matter how small it is, as long as these endpoints are distinct from each other, so as long as a is less than b, then the interval from a to b will contain rational points. So that's the meaning of density. So it's dense in the number line, but it's not all of the number line. So you may know an example already of an irrational number. So for instance, a very famous irrational number is the number pi. So pi is not rational. It can't be written as a fraction of two whole numbers. Another famous one is the square root of 2. The square root of 2 is also not rational. And in the case of the square root of 2, it's actually not very difficult to see that the square root of 2 is not rational. And so I want to show you the argument. I want to show you the argument not because it has that much to do with infinity, but for two reasons. The first is that it will involve a proof technique called proof by contradiction that we'll use several more times in the lecture series. The second reason is that I want you to understand where the rational numbers sit in relation to the real numbers. So as a consequence of this fact that we're about to prove, the rational numbers are a proper subset of the real numbers. This is our notation for the real line. It's all of the numbers on the number line. it will turn out that the rational numbers form a countable set. So this set will be countable, as we will prove shortly, whereas the real numbers, as we'll prove a bit less shortly, are an uncountable set. And the real numbers are the sort of archetypal set for a size of infinity called the continuum. So I think it's good to see that the rational numbers form a proper subset of the real numbers to motivate questions about whether the real numbers are of a higher order of infinity than the rational numbers, which will be one of the questions at the center of this lecture series. Let's look at the proof of that fact. So claim square root of 2 is not rational. The argument for this fact is going to involve a proof technique called proof by contradiction that we're going to use a few more times throughout the lectures. The idea is that if you want to prove that something is true, you start by assuming that it's false. And you show that the assumption that it was false entails a contradiction, entails something that you know cannot be true. So assume square root of 2 were rational. So then we can write square root of 2 equals m over n for whole numbers, m and n, with n non-zero. Then what we do is move the n to the other side, so we get n times the square root of 2 equals m, and then we square both sides. So we'll get n squared times square root of 2 squared, which is 2, equals m squared. Now, what we do is we appeal to something called the uniqueness of prime factorization, which you probably heard about in school. It's the idea that every positive whole number greater than or equal to 2 has a prime factorization, and that prime factorization is unique. That is, you can write that number, that integer, as a product of prime numbers, and there's only one way to write that number in that way. You cannot write a positive whole number greater than or equal to 2 as a product of primes in two different ways. When we prime factor n, we'll get 2 raised to some number. I'll call it k. And k may be 0 in the case that 2 does not occur in the prime factorization of n. In other words, if n is odd, then k will be 0, so that we get 2 to the 0, which is 1, which means that 2 does not appear in the prime factorization. And then times some other stuff. So other primes raised to some exponents, but those primes are not going to be 2. So other primes not including 2. And remember that we have the square here, so we have to square this quantity. Then we have times 2. And then we've got m squared. So we're going to prime factor m now. So again, so m will, the prime factorization will be 2 raised to some power, let's say L, that may be 0 in case 2 doesn't appear in the prime factorization of m, times some other primes, not including 2. Once again, we have to square. And now remember our rule for distributing exponents to a product. We distribute the exponent on the outside to each of the exponents in the product, and we multiply. So the result of this is that we'll have 2 to the 2 times k. Then again, times some other primes raised to what are now even exponents, but the primes themselves are all odd. That is, they're not 2. Times 2 again, from right here. And then we do the same thing on the right-hand side. Now this time we'll have 2 to the 2 times L times some other stuff, other primes that are not 2. Now I'm going to combine this factor 2 out here with these 2's inside of here. And when I do that, I add the exponents. So we'll get 2 to the 2k plus 1, and then we've got our other stuff still, times other stuff is equal to 2 to the 2l times other stuff. Notice that on the left and the right, we still have 2 prime factorizations. On the left here, we've got 2 raised to some power times a bunch of primes raised to some powers. And similarly on the right. So these are both prime factorizations. And we're asserting that they're prime factorizations of the same number. That's what this equal sign means. But notice that they can't be prime factorizations of the same number if prime factorization is unique, which we know it to be, because the exponents of 2 on the left and the right are different. This one is even, it's a multiple of 2. This one is one more than a multiple of 2, meaning that it's odd. So this contradicts the uniqueness of prime factorization, which is an absurdity. So we get a contradiction with something we know to be true. Therefore, our assumption, our original assumption, must have been false because it led us to something we know is not true. So this is not true, which means that our original claim was true. The square root of 2 is not rational. So just a little bit of history. This fact was discovered, I think, around 400 BCE by a group of mathematicians called the Pythagoreans. And it was a very distressing fact for them, so the legend goes, because they thought that all numbers were rational. And so it was very shocking for them to learn that if you take a square of side length 1 and you look at its diagonal, that its diagonal is not a rational number. They used a different argument, a sort of geometric argument, I believe. So now we know a little bit about our new set of rational numbers, Q, the set of fractions of whole numbers. We know that it's a subset of the real line, but it's not all of the real line. And we've also seen that it's dense in the real line. Now the next claim that I want to make is that our set of rationals is countable. So even though it looks on the face of it like a much larger set than the set of positive whole numbers, because after all it forms this dense subset of the real line, whereas the integers form this discrete set. Nonetheless, the two sets have the same size. And the idea for the proof is to first recall that the integer lattice, the set of all pairs, ordered pairs of whole numbers, is countable. And then note that every rational number, m over n, is built from a pair, an element of this set, say m comma n. That's an element of this set of ordered pairs of whole numbers. So maybe what we can do is take our set of rational numbers and put it in some kind of one-to-one pairing with the elements of the set z times z, the set of ordered pairs of whole numbers, where the correspondence is going to be m over n will get partnered with m comma n. So this is one idea you might initially have. If we could do that, it would show that this set of rational numbers is countable, because as we've already seen, this set on the right, the set of ordered pairs of whole numbers, can itself be paired with the set of positive whole numbers, which is what it means for it to be countable. Then we could sort of, as it were, combine these two pairings to get a pairing between the rationals and the natural numbers. It may immediately be clear what I mean by this, but in case it's not, suppose we have three sets and pairings between the first and the second, and between the second and the third. Well, then of course I can combine these two pairings to get a pairing between the first and the third. I take an element of the first set and I pair it with its partner's partner. So its partner is this dot, its partner's partner would be this dot in the third set. So the technical language for this is that this pairing property is transitive. So if I can pair the elements of A with the elements of B and the elements of B with the elements of C, then by the transitivity property I can pair the elements of A with the elements of C. So if we could establish this pairing, then we would have shown that the set of rational numbers is countable. Unfortunately, there are at least two problems with this particular pairing. And I invite you to pause the video and think about what the problems might be. So there are at least two problems. One is that, remember that in writing a rational number as a fraction of two whole numbers, we require that the denominator never be 0. This would mean that any ordered pair whose second coordinate is 0 would never get a partner in this set. For instance, 2 comma 0 would never be paired with anything because 2 over 0 is not a rational number. So first problem is that elements like 1 comma 0, minus 1 comma 0, 0 comma 0 never get partners. And perhaps the more serious problem is that although every rational number can be written as a fraction of two whole numbers, it's never uniquely written in that way. So for instance, 2 comma 1 and 4 comma 2 both get paired with the same rational number. Namely, what does this one get paired with? 2 over 1. This one gets paired with 4 over 2, which is the same thing as 2 over 1, namely 2. And remember that this is not permitted in pairing. So we don't permit two different elements of one set to be partnered with the same element in the other set. This pairing has to be sort of exclusive. But the good news is that these are both kind of the same problem, and it can be remedied easily. So if you think about, again, the integer lattice, z times z, if we're trying to pair up these points with a set of rational numbers, then the problem is both of these two issues here are a problem of having too many points. We have a bunch of points here that we don't need in order to represent the rational numbers. So for instance, 0, 0 doesn't get a partner in the other set. It's a point that we don't need if we're trying to represent the rationals. The point 1, 0 also doesn't represent a rational because its second coordinate is 0, which would lead to a 0 in the denominator of the rational number. The point 1, 1 does represent a rational number. It represents the number 1 because this is 1 over 1. What about the point 0, 1? This does represent a rational number, namely 0 over 1, the quotient of its two coordinates, so this is 0. Minus 1 over 1 does represent a rational number, so this is minus 1 over 1, which is minus 1. Then once again, we have something else. We have another point that we don't need. Minus 1, 0. It doesn't correspond to a rational number. So notice that I'm following the path of the spiral, which was the way that we found to count the integer lattice. So now we come down to this point, which is minus 1, minus 1. Then we come to the point minus 1, minus 1, which gives the fraction minus 1 divided by minus 1, which is positive 1. We've already seen positive 1. It was this first blue dot that we saw. This is an example of the second problem that we saw with our supposed pairing, that you can always write a rational number as a fraction of two whole numbers in many different ways. So the point minus 1 is also a point that we don't need. So it gets a red dot. Then we come to 0, minus 1. That corresponds to a rational number, namely 0, because it's 0 over minus 1. But we've already counted that rational number. So we're just going to ignore it. Then we keep following the spiral. This one is 1, minus 1. That does correspond to a rational number, but it's already counted because it corresponds to minus 1. It was counted right here. Then we come to a new rational number, 2 over minus 1, which is minus 2. That's a point we need to account for all of the rationals. So that's 2 over minus 1, which is minus 2. Then we come to another point that we don't need because its second coordinate is 0. Then we come to 2 over 1, which is a point that we need. And so we're going to continue in this way. And notice that as we spiral, we can still count. We're going to be counting the blue points, but we're going to be skipping the red points. So, for instance, this will be my first point. It will correspond to the rational 1. This will be my second point. It will correspond to the rational 0. This will be my third point. It will correspond to the rational minus 1. Then I'm going to skip all of these, and then my fourth rational number is going to be minus 2. My fifth will be 2. The next is one I count. This is 3 halves right here. Because its x coordinate is 3, its y coordinate is 2. So that's going to be my 4, 5, that's going to be my sixth rational number. So you can see that I am actually counting all of the rational numbers in this way because every rational number is represented by one of these integer points, by one of these lattice points. The only issue is that there were some points that we don't need, but we just skip them while we spiral. So we keep spiraling, count the points that we need, we skip the points that we don't need, and in this way we will count all of the rational numbers by counting some particular subset, namely the blue points, in the integer lattice. By spiraling through z times z and skipping points we don't need, we count all of the rationals. Thus, our set of rational numbers is countable. By the way, this idea of counting an infinite subset of a countable set by just skipping the elements that don't lie in the subset can be used generally to show that an infinite subset of a countable set is itself countable. So let's say that we have an infinite subset T of a countable set S. The assumption that S is countable means that there's a path that we can take through S that will give a label to any particular element of S. To count the elements of T, what we do is we take the exact same path, but we simply skip the elements of S that don't lie in T. So this would be my first element. I skip this element. This will be my second element, and so on. We know that we'll eventually label all the elements of T because the path itself labels all the elements of S, and T is a subset of S. We also know that we'll never run out of elements to label in T because T was infinite. So this is why countability is the lowest order of infinity. Although we won't know precisely what this means until we talk about how to tell when one infinite set has size smaller than another, perhaps you can already get a sense for why this fact about infinite subsets of countable sets being countable entails that countability is the lowest order of infinity. We denote this order of infinity with the first letter of the Hebrew alphabet, Aleph, and we put a 0 in the subscript. We'll say more about this order of infinity and its notation later. So our family of countable sets is growing. The most important countable set is, of course, the positive whole numbers. So this is our family of countable stuff. We've got n, we've got z, set of all whole numbers. Then we've got the integer lattice, set of all points in the plane whose coordinates are whole numbers. And now we've got q, the set of rational numbers. I think that's enough for a first lecture. In the next lecture, we'll start by adding one more set to our family of countable sets. That set will take us naturally into our first example of an uncountable set. That will be our first glimpse of an order of infinity greater than that of the positive whole numbers. So please join me in the next lecture.